Look up at the night sky. Those stars, those distant galaxies, they aren't just sitting still. Space itself is stretching, carrying everything in the universe further apart in a silent, relentless expansion. This isn't science fiction. It's the reality of our cosmos, a truth so strange it challenges everything we think we know about the fabric of existence. What if I told you that over the next few minutes, you'll uncover 30 mind-bending facts about the expansion of the universe, facts that will twist your perception of reality, make you question the very nature of space and time, and leave you staring at the night sky with entirely new eyes. Think about this for a second. The universe isn't just expanding, it's accelerating. The farther away a galaxy is, the faster it's racing away from us, as if some invisible force is pushing the cosmos apart at an ever-increasing speed. Scientists call this force dark energy, and to this day, it remains one of the greatest mysteries in all of physics. But that's just the beginning. The expansion of the universe isn't a gentle drift, it's a runaway train reshaping the destiny of everything we see. And here's the wildest part. If this keeps up, billions of years from now, distant galaxies will vanish from view entirely, their light stretched beyond the limits of detection, leaving future civilizations with a night sky far emptier than ours. This journey is about more than just facts, it's about peeling back the layers of reality to reveal the hidden mechanics of the universe. We'll explore how astronomers first discovered this cosmic expansion, why Einstein initially dismissed the idea and later called it his biggest blunder, and what the far future holds for a universe that never stops growing. Along the way, you'll encounter discoveries so strange they sound like fantasy, galaxies moving faster than light, phantom energy that could tear apart space-time itself, and the eerie possibility that we might one day be alone in an ever-darkening void. So settle in. By the time we're done, the night sky will never look the same to you again. In the late 1920s, astronomer Edwin Hubble made a discovery that shattered our understanding of the universe. Peering through the massive telescope at Mount Wilson Observatory, he noticed something peculiar about distant galaxies. They weren't just floating in place. Every single one was racing away from us, and the farther away a galaxy was, the faster it seemed to be moving. This wasn't just a few galaxies behaving oddly. It was a pattern, a cosmic law written in the light of the stars. Hubble's observations proved that the universe wasn't static, as even Einstein had once believed. It was stretching, growing, carrying galaxies along like raisins in an expanding loaf of bread. This revelation led to what we now call the Hubble constant, a number that tells us how fast the universe is expanding. At its core, it's a simple idea. For every 3 million light-years a galaxy is from us, it moves about 70 kilometers per second faster. But the implications were anything but simple. Hubble's work flipped astronomy on its head. Suddenly, the universe had a history, a beginning, and possibly an end. It was the first concrete evidence that space itself was dynamic, alive with motion on a scale we could barely comprehend. And yet, Hubble had no idea what was causing this expansion. That mystery would take decades to unravel, leading scientists down a path filled with even more surprises, like the existence of dark energy, a force so strange it makes the expansion accelerate. But let's not get ahead of ourselves. In that moment, Hubble's discovery was enough to rewrite the textbooks. Before him, many thought the Milky Way was the entire universe. After him, we knew we were just a tiny speck in an ocean of galaxies, all drifting apart in the vast, ever-growing expanse of space. It's humbling to think that a single observation, made nearly a century ago, could change our place in the cosmos so profoundly. And yet, Hubble's work was just the first clue in a mystery that's still unfolding today. Here's how we know the universe is stretching before our eyes. Light itself carries the proof. When astronomers peer at distant galaxies, they don't just see points of light. They see cosmic fingerprints stretched and distorted by the expansion of space. This phenomenon, called redshift, is one of the most crucial pieces of evidence we have for the universe's expansion. Imagine a fire truck speeding past you with its siren blaring. As it moves away, the sound waves stretch out, lowering the pitch, a familiar effect we call the Doppler shift. Now picture that same principle but with light. When a galaxy races away from us, its light waves get stretched, shifting toward the red end of the spectrum. The faster the galaxy moves, the redder its light appears. This isn't just a subtle change. Some of the most distant galaxies we've observed have their light stretched so dramatically that what was once visible or ultraviolet light reaches us as infrared, invisible to our eyes but detectable by telescopes. It's as if the universe is tugging on the very fabric of light, leaving behind a telltale sign of its relentless growth. And here's what's wild. This redshift isn't because galaxies are flying through space like that fire truck. It's because space itself is expanding between us and those galaxies, carrying them along like raisins in that cosmic loaf of bread. The farther the galaxy, the more space there is to stretch, and the more extreme the redshift becomes. This revelation didn't just confirm the universe was expanding, it gave us a way to measure that expansion. By analyzing how much a galaxy's light has redshifted, astronomers can calculate how fast it's moving away. And when they plot countless galaxies on a graph, a clear pattern emerges. The farther the galaxy, the greater the redshift and the faster it recedes. This relationship, first quantified by Hubble, is why we can say with certainty that the cosmos isn't static. It's alive, dynamic, and growing every second. But redshift does more than just prove expansion, it acts as a time machine. The light from those distant galaxies took billions of years to reach us, so when we observe their redshift, we're literally seeing the universe's expansion history written in light. Yet redshift holds even stranger secrets. Some galaxies are so far away that their light is redshifted to the point where it's barely detectable, not because they're dim, but because the expansion of space has stretched their light into near oblivion. One day, those galaxies will vanish entirely from our view, their light stretched beyond any wavelength we can observe. The universe's expansion isn't just a fact, it's a force that will eventually rewrite the night sky itself. But how do we know this expansion wasn't just some local phenomenon? What if space was stretching in one corner of the universe but not another? The answer comes from the oldest light in existence, the cosmic microwave background, a faint glow that fills every corner of the cosmos. Picture this, a snapshot of the universe when it was just 380,000 years old, a swirling sea of hot plasma cooling into atoms. In that moment, light broke free, traveling across space for billions of years until it reached us as a whisper of microwave radiation. This afterglow isn't uniform, it's speckled with tiny temperature variations, hotter and colder patches no larger than 100,000th of a degree. These fluctuations are the universe's baby pictures, revealing its earliest moments. The hotter spots, those are regions where matter was slightly denser, the seeds of future galaxies. The colder spots, areas where space was emptier. But here's the critical detail, these patterns are nearly identical no matter where we look. Whether we point our telescopes toward the constellation Orion or the far side of the Milky Way, the same telltale variations appear. That uniformity is proof the expansion wasn't isolated. It happened everywhere at once, stretching space like a cosmic drumhead vibrating in perfect harmony. The cosmic microwave background doesn't just confirm the Big Bang, it shows us how expansion imprinted itself on the fabric of reality. Those tiny temperature differences were stretched by the universe's growth, their wavelengths pulled longer over time. By measuring them, astronomers can calculate how fast space was expanding in those early moments, like rewinding a tape to see the first frames of the universe's story. And the numbers line up perfectly with Hubble's observations of galaxies rushing away. Two completely independent pieces of evidence, one from the dawn of time, the other from modern galaxies telling the same astonishing story. But the cosmic microwave background holds even deeper clues. The precise patterns of those fluctuations reveal something extraordinary: dark energy's fingerprints. The way those hot and cold spots are distributed across the sky matches predictions for an accelerating universe, one where expansion didn't slow down as expected but instead sped up over billions of years. It's as if the universe left us a coded message in its first light, waiting for us to decipher its hidden truths. And perhaps most mind-bending of all, we're still seeing new details in that ancient glow, clues that might one day reveal what happened even earlier in the universe's very first moments. So the next time you hear static on an old analog TV, remember about 1% of that noise isn't just random interference. It's the echo of creation itself, the faint afterglow of a universe being born, still whispering to us across the unimaginable gulf of time. For nearly 70 years, scientists thought they understood how the universe expanded, that gravity would eventually slow it down like a ball rolling uphill. Then, in 1998, two teams of astronomers made a discovery so shocking it upended everything. They were studying distant supernova exploding stars whose brightness should act as cosmic mile markers when they noticed something impossible. The universe wasn't just expanding, it was speeding up. Galaxies weren't merely coasting apart, some invisible force was pushing them faster, as if space itself had hit the gas pedal. This mysterious force got a name: dark energy, but its nature remains one of physics' greatest enigmas. Imagine blowing up a balloon with dots on its surface. Normally, you'd expect the dots to drift apart more slowly as the balloon inflates, but dark energy is like someone suddenly pumping air in faster, making those dots accelerate away from each other. Even stranger, dark energy isn't some minor player. It makes up roughly 68% of the universe's total energy budget, dwarfing everything we can see or touch. The discovery came from Type 1, a supernova, stellar explosions so consistent they're called standard candles. By measuring how bright these supernovae appeared versus how bright they should be, astronomers could gauge their distance. But the data revealed a bizarre inconsistency. The farthest explosions were dimmer than expected, meaning they were farther away than expansion models predicted. The only explanation: space had stretched more than anyone thought possible, accelerating over billions of years. It was like throwing a ball in the air and watching it shoot into space instead of falling back down. What makes dark energy even stranger is how it defies gravity. Normally, matter pulls things together, but dark energy seems to repel, pushing space apart. Some theories suggest it's woven into the vacuum of space itself, a property of nothingness that generates more nothingness as the universe expands. Others propose it's a dynamic field that changes over time, like an invisible fifth force of nature. But here's the unsettling part. If dark energy keeps strengthening, it could eventually tear atoms apart in a hypothetical Big Rip, ending the universe in absolute emptiness. Yet for all its dominance, dark energy leaves almost no trace. Unlike dark matter, which tugs on galaxies, dark energy's effects only appear on cosmic scales, visible only when you step back and see the universe as a whole. It's as if the cosmos hid its biggest secret in plain sight, waiting for us to notice the stars drifting faster into the void. And as we peer deeper into that void, one question lingers: what happens next in a universe where space itself is the ultimate runaway train? To visualize how the universe expands, picture a loaf of raisin bread baking in the oven. As the dough rises, every raisin moves away from every other raisin, not because they're traveling through the dough, but because the dough itself is stretching, carrying them along. Now imagine the raisins are galaxies and the dough is space itself. That's the best analogy we have for cosmic expansion. The key detail: no raisin is the center of this expansion. From any raisin's perspective, all others appear to be moving away, creating the illusion that it's at rest while everything else retreats. This reveals a fundamental truth about our universe. There is no privileged center, no fixed point from which everything is fleeing. Whether you're on Earth, a planet in the Andromeda galaxy, or a speck of dust in the farthest visible cluster, your view would be the same. All distant galaxies racing outward as space stretches between them. It's not that we're at the heart of some grand explosion. The Big Bang wasn't an explosion in space, but of space happening everywhere at once. Think of it like dots on an inflating balloon. If you mark two dots and blow air in, they drift apart not because they're moving across the balloon's surface, but because the rubber between them stretches. Add more dots and each one sees the same thing, every other dot receding. Now replace the balloon with three-dimensional space, and you've got the universe's expansion in action. This also explains why we can't point to where the Big Bang happened. It didn't occur at a single location, it occurred everywhere, a simultaneous stretching of the cosmos that continues today. Here's where it gets even wilder. Because space is expanding uniformly, the speed at which galaxies appear to move apart depends on distance. Two galaxies 1 million light-years apart will drift away slower than two galaxies 10 million light-years apart, not because they're moving faster, but because there's more space between them to stretch. This is why Hubble's law shows galaxies receding at speeds proportional to their distance. The farther they are, the more space multiplies between us, accelerating their apparent retreat. But this raises a haunting question. If everything is moving away, does that mean the universe is infinite? Or is it like the balloon's surface, finite but unbounded? Right now, we don't know. What we do know is that this expansion isn't just a curiosity, it's the backdrop against which all cosmic history plays out. Without it, stars wouldn't have formed, galaxies wouldn't have clustered, and we wouldn't be here to ponder it. The raisin-bread universe isn't just expanding, it's the reason we exist at all. Among the countless stars that flicker in the night, some hold a secret, a cosmic consistency so precise they act as lighthouses in the vast ocean of space. These are Type 1, a supernova, stellar explosions so uniform in brightness that astronomers call them standard candles. Picture this, a white dwarf star siphoning material from a companion until it hits a critical mass, triggering a runaway nuclear explosion so powerful it briefly outshines entire galaxies. But here's what makes them invaluable. Every single one of these supernova peaks at nearly identical luminosity. This predictability transforms them into cosmic yardsticks. When astronomers spot a Type 1, a supernova in a distant galaxy, they know its true brightness. By comparing that to how dim it appears from Earth, they can calculate exactly how far away it is, like judging a distant lighthouse's distance by how faint its beam looks. But these stellar explosions do more than measure distance. They reveal how space itself has stretched over time. Because light from the most distant supernova took billions of years to reach us, their observed brightness tells us how much the universe has expanded during that journey. The real breakthrough came when scientists noticed something odd. The farthest supernova were consistently dimmer than expected, suggesting they were even more distant than standard expansion models predicted. This wasn't a minor discrepancy. It was evidence that the universe's expansion wasn't slowing down as gravity would dictate, but speeding up. Imagine tossing a ball in the air and watching it shoot upward faster instead of falling back. That's the baffling reality dark energy introduced, and Type 1, a supernova, were the first to expose it. What's astonishing is how much these explosions reveal despite their brevity. A supernova might blaze for weeks before fading, but in that short window, it encodes the history of cosmic expansion. By cataloging hundreds of them across different distances, astronomers have built a timeline of the universe's growth, one that shows acceleration beginning around 5 billion years ago. Before that, gravity's pull was dominant. Afterward, dark energy took the wheel. Yet even standard candles have quirks. Dust between galaxies can dim their light, mimicking greater distances. To compensate, scientists cross-check supernova data with other measurements: redshift, galaxy clusters, the cosmic microwave background. It's like solving a puzzle where every piece must align. And when they do, the picture is undeniable. The universe isn't just expanding, it's accelerating into a future we're only beginning to understand. These stellar explosions are more than just tools, they're time capsules. Each one captures a moment in cosmic history, a snapshot of space stretching under dark energy's influence. And as we discover more of them, we edge closer to answering the biggest question of all: where is the universe speeding to, and what awaits at the end of the ride? Right now, cosmology faces a puzzle so perplexing it's shaking the foundations of modern astronomy. It's called the Hubble Tension. Here's the problem. When scientists measure how fast the universe is expanding using two of our most trusted methods, they get different answers. Not just slightly off, but enough to suggest something fundamental in our understanding might be missing. One method relies on the cosmic microwave background, that ancient light from the infant universe, while the other uses the brightness of distant supernovae. Both approaches are meticulous, both backed by decades of evidence, yet they stubbornly refuse to agree. Let's break it down. The cosmic microwave background method, courtesy of the Planck satellite, gives us an expansion rate of about 67 kilometers per second per megaparsec. Meanwhile, supernova observations peg it closer to 73. That 6-kilometer gap might sound small, but in the precision-driven world of cosmology, it's a chasm. Imagine two clocks, both built by master watchmakers. One ticks slightly faster than the other. Over days, the difference is negligible. Over years, it's noticeable. But over billions of years, that tiny discrepancy rewrites cosmic history. What makes this conflict so thrilling is what it implies: either one of our measurement techniques is flawed in ways we haven't caught, or our standard model of cosmology, the very framework we use to understand the universe, is incomplete. Some theorists suggest unseen particles or new forces could be tweaking the expansion rate. Others propose dark energy isn't constant but evolves over time, throwing off our calculations. There's even wilder speculation. Could multiple universes with different physics be subtly influencing ours? The stakes couldn't be higher. If the Hubble tension holds, it could mean rewriting textbooks to include physics beyond Einstein's relativity or the standard model of particle physics. Picture it like discovering a hidden ingredient in a recipe you've perfected for years, one that changes the entire dish. Right now, astronomers are racing to solve this mystery, using everything from gravitational waves to quasars as cross-checks. And while the answer remains elusive, one thing's certain: the universe loves keeping us on our toes, revealing just enough to remind us how much we have yet to learn. The universe had a growth spurt, one so extreme it makes today's expansion seem sluggish by comparison. Within the first trillionth of a second after the Big Bang, space didn't just expand, it exploded outward at a rate beyond imagination, doubling in size at least 60 times over in a blink. This was cosmic inflation, a brief but universe-shaping event that answers one of cosmology's biggest puzzles. Why does the cosmos look so similar in all directions? Picture stirring cream into coffee. No matter where you dip your spoon, the mixture looks uniform. That's our universe on a grand scale, a cosmic brew where temperatures and densities vary by less than 1 part in 100,000 across billions of light years. Without inflation, such uniformity would be impossible. Regions now on opposite sides of the visible universe were once close enough to exchange heat, evening out their properties before inflation flung them apart faster than light could bridge the gap. It's like two artists starting with identical blueprints on neighboring canvases, then someone suddenly stretching those canvases across a continent. The matching patterns remain, but the artists can no longer compare notes. Gravity waves could hold the smoking gun for inflation. Theory predicts these ripples in space-time would have been generated during inflation's violent stretching, leaving faint imprints in the cosmic microwave background. Imagine dropping a pebble into a pond. The expanding ripples would freeze if the water suddenly turned to ice. Inflation's gravity waves would have left similar, frozen patterns in the early universe's plasma, detectable as a faint swirl in the polarization of ancient light. Finding this signal would be like uncovering the cosmic equivalent of dinosaur footprints, direct evidence of an event that reshaped everything. Here's where it gets stranger. Inflation wasn't just a one-time event. Some theories suggest it never truly stopped. While it ended in our observable universe, other regions of space might continue inflating eternally, spawning endless bubble universes with different physical laws. It's a dizzying thought. Our entire cosmos could be one bubble in an infinite froth of universes, each with its own unique reality. And if gravity waves confirm inflation, it won't just solve mysteries, it'll open doors to questions we haven't even dared to ask yet. What makes inflation so revolutionary isn't just its speed, it's how it turned quantum fluctuations into galactic seeds. Microscopic density variations, smaller than an atom, were stretched to cosmic proportions during inflation, eventually collapsing under gravity to form galaxies. Those same imperfections are why you exist. Without them, matter would be spread perfectly evenly, and stars and planets like Earth could never have formed. Inflation didn't just make the universe big, it made it lumpy in just the right way for life to emerge. And if we can decode its echoes, we might finally understand why the cosmos is tailor-made for curiosity. Where does the universe's runaway expansion lead? The answer lies in one of three cosmic finales, each more dramatic than the last. The first, called the Big Freeze, unfolds like a slow-motion fade to black. As expansion continues, galaxies drift so far apart that their light can no longer reach us. Stars burn out, black holes evaporate, and temperatures plunge toward absolute zero. The cosmos becomes a vast, dark graveyard where even time loses meaning. A silent, eternal chill where nothing stirs. It's the most widely accepted scenario, a whisper of heat death where entropy wins and all energy dissipates into an equilibrium so perfect that nothing can ever happen again. But dark energy could rewrite that ending into something far more violent, the Big Rip. Imagine the universe's expansion accelerating so fiercely that not even galaxies or solar systems remain bound together. First, galaxy clusters would tear apart, then individual galaxies. Stars would rip from their orbits, planets would unravel, and finally, even atoms would be shredded as the repulsive force of dark energy overpowers every fundamental force in nature. Space itself would fracture, leaving behind a void where not even the fabric of reality survives. This apocalyptic scenario hinges on dark energy growing stronger over time, a force so relentless it could reduce existence to infinite, disconnected particles. Then there's the cosmic pendulum swing, the Big Crunch. If dark energy weakens and gravity regains dominance, expansion could reverse, pulling everything back together in a mirror image of the Big Bang. Galaxies would collide, temperatures skyrocket, and spacetime itself crumple into a singularity, a fiery collapse where the universe ends as it began, compressed into an unimaginably dense point. Some theories even suggest this could trigger a new Big Bang, birthing another universe in an endless cycle of expansion and contraction. The choice between these fates hinges on unknowns, dark energy's true nature, the universe's curvature, and whether gravity's grip can ever counter expansion. Right now, the evidence leans toward the Big Freeze, but the cosmos has surprised us before. One thing's certain, the universe's finale won't be quiet surrender or simple repetition. It'll be a climax written in the deepest laws of physics, playing out over timescales so vast they dwarf human history. And while we may never witness that ending, the clues we uncover today will decide which story the cosmos is telling: a slow fade, a violent rupture, or a rebirth from the ashes. Peering into the night sky feels like looking through a window with infinite depth, but even the cosmos has its blinds. There's a fundamental limit to how far we can see. a cosmic horizon currently sitting about 46 billion light-years away in every direction. This isn't just a distance marker. It's the ultimate barrier, the edge of the observable universe. Everything beyond that point isn't merely too dim or too distant. Its light hasn't had enough time to reach us since the Big Bang, no matter how powerful our telescopes become. Here's the twist: that 46 billion light-year figure seems impossible when you consider the universe is only 13.8 billion years old. How can we see objects farther away than light could have traveled in that time? The answer lies in expansion itself. Space has stretched so dramatically since the Big Bang that light emitted from those distant regions has been carried along like a leaf caught in a rushing river. While the light has been traveling toward us for billions of years, the space behind it kept expanding, lengthening its journey and redshifting its wavelengths into oblivion. This creates a paradox. We live inside a bubble where the laws of physics allow us to see just 4% of the universe's true scale. Every second, as expansion accelerates, that horizon grows more restrictive. Galaxies now crossing that 46 billion light-year threshold won't vanish immediately. Their light, already en route, will continue reaching us for billions of years. But any new light they emit from this moment onward will be stretched beyond detectability, leaving them eternally stranded in the darkness beyond our view. Imagine standing on a shoreline where the tide is permanently receding. Each wave that reaches you represents ancient light from galaxies now permanently beyond reach. The sand beneath your feet, that's the observable universe, its borders shrinking relative to the vastness beyond. In time, even our closest galactic neighbors will slip over that horizon, their light stretched into wavelengths too long for any instrument to catch. Future astronomers might witness a night sky where only a handful of gravitationally bound galaxies remain, the rest erased not by distance but by the relentless stretching of space itself. This horizon isn't just a curiosity, it defines the ultimate limit of human knowledge. No signal, no probe, no telescope can ever breach it. We're like sailors charting an ocean that grows faster than we can explore, where distant shores vanish before we even glimpse them. And yet, within our shrinking island of visibility, the universe keeps whispering its secrets if only we learn how to listen. Even as the universe stretches galaxies apart on cosmic scales, some neighbors are destined for a spectacular collision, and our own Milky Way is no exception. Meet Andromeda, the colossal spiral galaxy hurtling toward us at nearly 300,000 kilometers per hour. Despite the universe's expansion, gravity's grip is strong enough to pull us together across 2.5 million light-years of space. In about 4 billion years, our galaxies will begin a cataclysmic dance, twisting and merging over eons until they form a single, gargantuan elliptical galaxy, an event astronomers poetically call Milkomda. This might seem impossible given everything we've learned about cosmic expansion. Distant galaxies are racing away, but Andromeda and the Milky Way are part of a local group, a cluster bound by gravity's unbreakable chains. Think of it like a rubber sheet being stretched. While the sheet expands, any objects tied together with string won't drift apart. Gravity acts as that string, tethering galaxies close enough to resist the universe's outward pull. In fact, nearly all galaxies exist in groups or clusters where gravity dominates, creating pockets of order amidst the cosmic sprawl. The collision won't be the violent crash you might imagine. Galaxies are mostly empty space, their stars so widely scattered that direct impacts are vanishingly rare. Instead, their gravitational forces will warp each other's shapes, flinging stars into new orbits while interstellar gas collides, igniting bursts of new star formation. Picture two crowds of people walking through each other in a vast field. Most individuals pass by untouched, but the swirling patterns they create together transform the entire scene. Yet this merger is just one example of a broader cosmic phenomenon: galactic cannibalism. Larger galaxies often absorb smaller ones, growing like celestial predators. The Milky Way itself has already consumed dozens of dwarf galaxies, their stars now strewn through our galactic halo. Andromeda's past is even more violent. Its halo holds the shredded remains of galaxies it devoured over billions of years. These mergers aren't destruction, they're evolution, reshaping galaxies into new forms while recycling material for future stars. What's truly humbling is the timescale. While the first close pass happens in 4 billion years, the full merger will take another 2 billion years to complete. By then, Earth's fate is uncertain. Our planet might be scorched by a swelling sun long before the galactic cores collide. But the universe will have gained a spectacular new island of stars, a testament to gravity's power to create even as the cosmos expands. So while dark energy pushes most galaxies away, our local corner of the universe remains a bustling neighborhood where close encounters still shape the future. In the quiet vacuum of space, where classical physics tells us nothing should exist, lies one of science's most baffling failures, a miscalculation so vast it's been called the vacuum catastrophe. Quantum theory predicts that empty space isn't truly empty but seething with virtual particles popping in and out of existence, a quantum froth that should generate an immense energy density. Calculate that energy, and the numbers are staggering around 10 to the power of 112 joules per cubic meter. Now measure the actual energy driving cosmic expansion, dark energy, and the result is a whisper in comparison, just 10 to the power of -9 joules. That's a discrepancy of 120 orders of magnitude, the equivalent of predicting a tidal wave and getting a single drop of water instead. This isn't just a rounding error, it's physics' most embarrassing prediction, a disconnect so severe it suggests something fundamental is missing from our understanding of the universe. Imagine forecasting a hurricane based on atmospheric data, only to step outside and find a breeze barely rustling the leaves. The dissonance arises because quantum field theory and general relativity, our two most successful frameworks for describing reality, clash spectacularly when it comes to the vacuum. Quantum mechanics treats space as a bubbling cauldron of energy, while relativity sees it as a smooth, stretchable fabric. When their predictions collide, the gap is cosmic. Efforts to reconcile this have spawned wild theories. Some propose an unknown symmetry cancels out most vacuum energy like perfectly balanced scales. Others suggest dark energy isn't constant but dynamic, evolving over time to settle at its oddly tiny value. The most radical idea that we're seeing evidence of a multiverse where countless universes spawn with random vacuum energies, and we just happen to live in one where the number is bizarrely small, allowing galaxies and life to form. The vacuum catastrophe isn't just academic, it's a glaring signpost pointing to undiscovered physics. Solving it might require reimagining gravity, quantizing space-time, or accepting that empty space hides secrets far stranger than we've dared to guess. Until then, it remains a humbling reminder, even our best theories are sketches of a reality we've only begun to trace. The universe doesn't just stretch space, it stretches time itself. When astronomers observe the most distant supernova or quasars, they're not just seeing light redshifted by expansion. They're witnessing time dilation, a bizarre effect that makes cosmic events appear to unfold in slow motion from our vantage point. It's as if the universe has a built-in playback setting where the farther away an event is, the more its clock seems to drag compared to ours. Picture a firework exploding in extreme slow motion, its brilliant flare crawling across the sky at half speed. That's essentially what happens when we watch a supernova billions of light years away. As the light travels through expanding space, its wavelengths stretch, not just altering color, but also extending the duration between light pulses. A cosmic explosion that lasted 1 week in its own time frame might appear to play out over 2 weeks in our telescopes. This isn't an illusion. It's a direct consequence of relativity meeting cosmic expansion, warping both space and time on intergalactic scales. The mathematics behind this is elegant. just as redshift stretches light waves by a factor we call 1 plus z, where z is the redshift value, time dilation stretches observed events by that same factor. A galaxy at z equals 1 appears to tick half as fast as our local time. At z equals 2, it's 3 times slower, like watching a movie at 1/3 normal speed. The most distant known galaxies with z values above 10 unfold at such a glacial pace that their entire star formation histories appear drawn out across eons of our observation time. This phenomenon gives astronomers a powerful tool. By comparing how fast distant supernovae fade versus nearby ones, they can measure time dilation directly, a crucial confirmation that expansion affects the fabric of reality itself, not just light. It also solves a practical puzzle. Without accounting for this effect, the brightness variations of faraway cosmic explosions wouldn't match predictions. The universe doesn't just show us its pass through light travel time, it plays that passed back in altered speed, like a cosmic tape recorder running at the wrong RPM. Here's what's truly mind-bending. This time warping means we're not just looking back in time when we observe distant objects, we're looking at time that fundamentally flowed differently in those regions. A billion-year-old galaxy at z equals 2 didn't just exist when the universe was younger. It evolved at a different rate relative to us. The very ticking of atomic clocks there was out of sync with ours before their light even began its journey. This relativity of time isn't just philosophical, it's etched into every photon that reaches us from the cosmic deep. Yet time dilation has limits. Beyond a certain distance, expansion accelerates so much that light from those regions will never reach us at all. Their clocks don't just run slow, they become frozen from our perspective, their final moments stretched into eternity. It's a sobering thought. Some parts of the universe are already so far gone that their time might as well have stopped for us, their stories forever paused mid-sentence in the cosmic archive. What if the very fabric of space itself holds the key to dark energy's mystery? At the smallest scales imaginable, far below the realm of atoms or even subatomic particles, space-time isn't the smooth, placid surface we picture. It's a turbulent sea of quantum foam, where virtual particles constantly flicker into existence and vanish in less than an eye blink. These fleeting fluctuations aren't just theoretical, they generate an energy so immense that, if left unchecked, they'd warp the universe beyond recognition. Yet somehow, against all expectation, their net effect appears almost negligible on cosmic scales. This paradox is where dark energy might be hiding in plain sight. Imagine shaking a soda bottle furiously, then slowly unscrewing the cap. The froth that erupts isn't random chaos. It follows physical laws we can measure, even if the bubbles seem chaotic up close. Quantum foam behaves similarly, with particle-antiparticle pairs appearing and annihilating trillions of times per second in every cubic centimeter of space. According to quantum field theory, this frenzy should contribute an enormous vacuum energy density, enough to curve spacetime violently or even tear it apart. Yet when we measure the actual energy driving cosmic acceleration, it's a whisper compared to those predictions. So where's the disconnect? Some theorists propose dark energy isn't some exotic new force, but the collective sigh of this quantum foam after gravity cancels out most of its energy. Picture two singers hitting identical notes exactly out of phase. Their sound waves cancel each other, creating silence where there should be noise. If spacetime's underlying symmetries work similarly, they could suppress quantum foam's wild energy, leaving behind only the faintest residual pressure, just enough to explain dark energy's subtle push. Others take a bolder approach, suggesting dark energy represents quantum foam's influence leaking into our classical universe. In this view, the foam isn't perfectly balanced. Tiny asymmetries allow its energy to bubble up, stretching space from within like yeast puffing up dough. Supporting this idea, some models show how quantum fluctuations at the universe's birth could have imprinted irregularities that eventually manifested as dark energy's repulsive force. It's as if the cosmos baked its own expansion into spacetime's quantum recipe from the very first moments. The most radical theories go further, proposing dark energy signals our universe brushing against others in a hidden multiverse. Quantum foam's turbulence might be the overlap between these realities, their interactions generating energy that appears as cosmic acceleration in our dimension. Think of it like ocean waves crashing against a reef. The spray that flies upward represents dark energy, a byproduct of invisible forces colliding just beyond our perception. Yet for all their creativity, these ideas highlight a deeper truth. We're grasping at a phenomenon that defies conventional frameworks. Quantum foam's energy exists mathematically, but its observable effects remain elusive, like a shadow that vanishes when you turn on the light. Solving this riddle might require reimagining gravity itself or accepting that space-time is far stranger than relativity predicts. Until then, quantum foam remains both a tantalizing clue and a frustrating red herring in the hunt for dark energy's true nature. One thing's certain: if the answer lies in these microscopic fluctuations, it would unite the universe's largest and smallest scales in a way Einstein never dreamed. The same quantum jitters that shape atoms could be steering galaxies, a cosmic feedback loop where the infinitesimal controls the infinite. And that's a connection worth chasing, no matter how frothy the path may be. Back in the universe's infancy, before stars or galaxies existed, space was a roiling sea of plasma so dense that light couldn't travel more than a hair's breadth before scattering. Within that primordial soup, sound waves raced outward at half the speed of light, not the kind of sound we hear, but pressure waves rippling through the hot, compressed matter. These weren't fleeting vibrations, they were universe-shaping tremors, echoes of the Big Bang itself, and they left behind a cosmic fingerprint so precise we can still read it today in the way galaxies cluster across the sky. These ancient pressure waves, known as Barrian acoustic oscillations, work like a ruler etched into the fabric of the cosmos. Picture dropping a pebble into a pond. The ripples spread outward in perfect rings before freezing in place. In the early universe, gravity pulled matter toward the crests of those waves, while radiation pressure pushed it away. For 380,000 years, this tug-of-war created alternating shells of dense and sparse matter. Then, as the universe cooled and atoms formed, the waves froze mid-ripple, locking their patterns into the distribution of matter forever. Today, we see those frozen ripples in galaxy surveys. If you mapped the positions of millions of galaxies, you'd notice they're slightly more likely to be separated by around 500 million light-years, the exact wavelength of those primordial sound waves stretched by cosmic expansion. This isn't random noise, it's the universe's way of handing us a calibrated measuring stick. By comparing the apparent size of these oscillations at different distances, and thus different eras, we can track precisely how space has stretched over billions of years. What makes Barrian acoustic oscillations so powerful is their independence from other methods. While supernovae rely on understanding stellar explosions and the cosmic microwave background requires decoding ancient light, these frozen sound waves depend only on gravity and simple physics. They're a cosmic constant, immune to the quirks of dust or stellar evolution. When combined with other measurements, they've helped pin down the universe's expansion rate with unprecedented precision. And they're one of the key reasons we're so confident dark energy is real. Yet these oscillations hold deeper secrets. Their precise scale reveals not just how fast the universe expands, but also the curvature of space itself. If measurements show the ripples appear larger or smaller at certain distances than expected, it could hint at exotic physics, extra dimensions, modified gravity, or even clues about inflation's earliest moments. They're like hieroglyphs carved into the cosmos, telling a story that began with a bang and continues to unfold in the silent, stretching dark between galaxies. The next time you look at a star chart or a galaxy map, remember, you're not just seeing points of light, You're witnessing the aftermath of a primordial symphony where the notes were pressure waves and the score was written in the first microseconds of existence. And as we keep listening, those echoes may yet reveal the universe's next great mystery. Among all possible cosmic fates, none is more violent than the phantom energy scenario, a hypothesis so extreme it turns the universe's expansion into an executioner. Picture dark energy not as a steady force, but one that grows stronger over time, its density escalating until it overpowers every binding force in nature. Gravity, electromagnetism, even the nuclear glue holding atoms together, all would be rendered useless in the face of this relentless acceleration. The result: a big rip where space itself becomes a shredding machine, tearing apart galaxies, stars, planets, and finally, the very fabric of matter. The mathematics behind this nightmare reveal its eerie plausibility. Normally, dark energy's density remains constant as the universe expands like a tank of gas that never depletes no matter how far you drive. But phantom energy suggests something far worse, a tank that magically gains fuel the emptier it gets. If dark energy's equation of state parameter dips below -1, its pressure doesn't just repel, it intensifies with expansion, creating a feedback loop where every stretch of space generates more repulsion. It's the cosmic equivalent of a snowball rolling downhill, growing larger and faster until it obliterates everything in its path. Here's how the end would unfold. First, galaxy clusters already drifting apart would be yanked violently away from each other. Then individual galaxies would disintegrate as stars are ripped from their orbits. Next, solar systems would fly apart, planets torn from their suns. In the final minutes, the nightmare turns personal Earth's gravity would fail to hold itself together, mountains crumbling as the planet explodes outward. In the last microseconds, atoms themselves would be shredded, protons and electrons torn apart as the electromagnetic force loses its grip. The universe wouldn't just fade, it would be annihilated from the bottom up, reduced to a sea of disconnected particles unable to ever interact again. What makes phantom energy especially chilling is its timeline. Unlike the slow heat death of the Big Freeze, the Big Rip could occur within a finite window. Some models suggest as little as 22 billion years from now, a blink in cosmic terms. Astronomers might even see it coming. Tens of millions of years before the end, galaxies beyond our local group would vanish from view, their light stretched beyond detectability. Then closer neighbors would disappear until only the Milky Way's corpse remained visible in an otherwise black sky. Yet the Big Rip isn't just doom-mongering, it forces us to confront dark energy's true nature. Most observations align with a constant dark energy density, but phantom energy remains mathematically possible. Future measurements of supernovae and baryon acoustic oscillations could reveal whether dark energy's equation of state is creeping toward that catastrophic threshold. The fact that we're even debating such extremes shows how little we grasp the force shaping the universe's destiny. Perhaps the most unsettling thought isn't the rip itself, but what it implies about reality. If space can stretch so violently that it overrides quantum bonds, then the cosmos is far more fragile than we imagined. The same expansion that created galaxies might one day unmake them, proving that the universe's greatest creative force could also be its ultimate destroyer. For now, phantom energy remains a haunting hypothesis, but its mere possibility reminds us that the cosmos plays by rules we're still struggling to read. Cosmic inflation didn't just shape our universe, it might have spawned countless others, each with its own unique laws of physics. Imagine blowing soap bubbles in a breeze. Some pop instantly, some drift away, and others merge into larger bubbles. Inflation theory suggests something similar happened on a cosmic scale. Our universe could be one bubble in an endless froth of universes, each with its own distinct properties. This isn't science fiction. It's a direct consequence of inflation's relentless expansion, where quantum fluctuations in the early universe grew into separate realms with different physical constants. Think of it like a cosmic bakery where the dough keeps rising forever, but instead of a single loaf, you get an infinite number of breads, some sour dough, some rye, others with ingredients you've never heard of. In this multiverse scenario, the dough is the inflating space-time, and the bubbles are regions where inflation stopped, giving rise to stable universes like ours. The catch: the rules inside each bubble could be wildly different. One might have stronger gravity, making stars burn out in milliseconds. Another could have no electromagnetic force, preventing atoms from forming at all. We just happen to live in a bubble where the constants allow galaxies, planets, and life to exist, a concept called the anthropic principle. The evidence for this mind-bending idea lies in the fine-tuning of our universe. Gravity's strength, the mass of electrons, even the energy density of empty space. If any of these values were slightly different, life as we know it would be impossible. The multiverse offers an explanation. With infinite variations, some bubbles inevitably hit the jackpot. It's like buying every possible lottery ticket. Sooner or later, one will match the winning numbers. Here's where it gets even stranger. Some bubble universes might be so close that their gravitational fields lightly tug on ours, leaving faint imprints in the cosmic microwave background. Others could collide with ours, creating bizarre scars in the sky, anomalies where the laws of physics suddenly shift. Scientists have searched for these signatures, though none have been confirmed yet. But the mere possibility reshapes how we view reality. What we call the universe might just be our local neighborhood in a sprawling, unobservable megacosmos. Critics argue the multiverse is untestable, more philosophy than science. Yet inflation's mathematics naturally leads there, and some versions of string theory require it. If future telescopes detect unexplained patterns in the microwave background or gravitational waves with odd frequencies, we might glimpse our cosmic siblings for the first time. Until then, the multiverse remains the ultimate what if, a reminder that the universe's greatest mysteries might lie beyond the horizon of what we can see. Einstein's equations of general relativity held a hidden surprise, one so unsettling that even he struggled to accept it. When he published his theory in 1915, it described gravity as the curvature of spacetime, but it also contained a shocking implication: the universe couldn't stay still. Like a house built on a slope, the cosmos would either collapse under its own gravity or expand outward with no in-between. This flew in the face of everything astronomers believed at the time. The Milky Way was thought to be the entire universe, and the stars within it appeared fixed, eternal. So Einstein did something uncharacteristic. He tweaked his own masterpiece, adding a fudge factor he called the cosmological constant. A kind of anti-gravity, this mysterious term counterbalanced cosmic collapse, propping the universe into a static, unchanging state. For over a decade, Einstein defended this idea, even as evidence mounted against it. Then, in 1929, Edwin Hubble's observations of receding galaxies shattered the myth of a static universe. Space wasn't standing still, it was stretching, carrying galaxies along like driftwood on a rising tide. Einstein famously called the cosmological constant his greatest blunder, dismissing it as unnecessary. But history would have the last laugh. 70 years later, when astronomers discovered that the universe's expansion wasn't just continuing but accelerating, they realized Einstein's blunder wasn't a mistake at all. It was a near-prophetic glimpse of dark energy. The irony is exquisite. The cosmological constant had been lurking in Einstein's equations all along, a mathematical term representing the energy of empty space. Remove it and the universe behaves one way. Include it and you get repulsive gravity, an outward push woven into the fabric of reality. Modern measurements show dark energy's effects match the cosmological constant's predictions with eerie precision. It's as if Einstein accidentally scribbled the answer to a puzzle no one had even posed yet then threw it away, thinking it worthless. What makes this story so compelling isn't just the twist of scientific fate. It's the lesson hidden within. Even geniuses can misread their own discoveries. Einstein's resistance to an expanding universe wasn't just stubbornness, it reflected the limits of human intuition when faced with cosmic truths. The universe didn't care that static models were comforting or familiar. It obeyed deeper laws, ones that eventually forced us to rewrite the story of reality. Today, the cosmological constant is back at the heart of cosmology, not as a fix for a static universe, but as the leading explanation for dark energy's relentless push. And while Einstein might have rejected it twice, first as unnecessary, then as implausible, his blunder now stands as one of science's most humbling reminders. Sometimes the truth hides in plain sight, waiting for the right moment to reveal itself, and sometimes it takes decades for even the greatest minds to recognize the clues they've left behind. We like to think of our place in the universe as ordinary, but the cosmos has a way of humbling our assumptions. Recent observations reveal that our Milky Way galaxy sits inside an enormous bubble of nothingness, the KBC void, named after astronomers Keenan, Barger, and Cowie, who identified it. Spanning over 2 billion light-years across, this vast cosmic desert contains far fewer galaxies than expected, making our galactic neighborhood eerily sparse compared to the dense walls of galaxy clusters surrounding it. This discovery appends a fundamental principle astronomers have relied on for decades, the cosmological principle, which states that on large scales, the universe should look roughly the same no matter where you are. If true, expansion rates and matter distribution should be uniform when averaged across vast distances, but the KBC void throws a wrench into that assumption. Imagine stepping outside to find your house sitting alone in the middle of a 100-mile-wide empty field while bustling cities loom on the distant horizon. That's essentially our cosmic predicament, a rare underdense region where matter is suspiciously scarce. The implications are profound. If we're inside a void, measurements of the universe's expansion rate could be skewed. Light from distant supernovae passing through this underdense region would behave differently than light traveling through denser cosmic highways, potentially explaining discrepancies like the Hubble tension. It's like trying to judge the speed of cars on a highway while standing in a tunnel. Your limited vantage point distorts the true picture of traffic flow. Some theorists suggest that living in a void might mean we've underestimated how fast the universe is expanding beyond our sparse bubble. What's even stranger is how rare voids like this should be. Simulations of cosmic structure predict that voids of this scale are exceptionally unlikely, less than a 1 in 10,000 chance. Yet here we are, floating in one of the largest known empty regions in the observable universe. This raises an unsettling question. Is our position special after all, despite centuries of insisting otherwise? The Copernican principle, which holds that Earth holds no privileged place in the cosmos, suddenly feels less certain when we're sitting in a galactic anomaly vast enough to house thousands of Milky Ways end to end with room to spare. The KBC void isn't completely empty. Our local group of galaxies drifts within it like a handful of marbles in an otherwise vacant stadium. But compared to the dense galactic superclusters beyond its edges, the difference is stark. Maps of the universe show intricate filaments of galaxies weaving around these voids, tracing a cosmic web where matter clusters like foam on an ocean's surface. Our void just happens to be one of the biggest bubbles in that foam. Whether this changes our fundamental understanding of the universe remains to be seen. But it serves as a crucial reminder when we measure the cosmos. We're always seeing it from one particular vantage point. And if that vantage point turns out to be an outlier, our cosmic maps might need more than a few adjustments. For now, the KBC void stands as both a mystery and a challenge, daring us to question what we think we know about the universe's true structure. What if one of physics' most sacred constants wasn't so constant after all? The speed of light, approximately 300,000 kilometers per second in a vacuum, anchors Einstein's theory of relativity and underpins our entire understanding of cosmic distances and time. Yet a radical idea suggests this universal speed limit might have been higher in the early universe, a tweak that could resolve glaring inconsistencies in our measurements of cosmic expansion. This isn't idle speculation. Some theorists argue that a variable speed of light offers an elegant solution to the Hubble tension without invoking unknown physics like dark energy or extra dimensions. Picture this: moments after the Big Bang, when the universe was a seething plasma of energy, light might have traveled faster than today's accepted value. Just as sound moves quicker through water than air, light's speed could have depended on the density and structure of the primordial cosmos. In this scenario, photons racing through that hotter, denser medium wouldn't have faced the same constraints they do now. The implications are staggering if true. It would mean the early universe's expansion didn't require inflation to explain its uniformity. Distant regions could have exchanged information faster than standard physics allows, naturally smoothing out temperature variations without the need for a mysterious inflationary field. Supporters of this idea point to subtle anomalies in the cosmic microwave background. Certain patterns in that ancient light appear smoother than inflation alone can explain, as if something helped even out temperatures across vaster distances than light speed should permit. A faster speed of light in the early universe would bridge that gap effortlessly. It's like discovering that an athlete who supposedly ran a mile in 4 minutes actually had a head start suddenly. Their feat makes sense without rewriting the rules of human physiology. Critics counter that altering light speed unravels too much established physics. Einstein's relativity hinges on light speed's constancy. Change that, and everything from particle physics to GPS satellite synchronization collapses. But proponents argue relativity might still hold locally. Light speed could have been universally higher in the past without violating the laws governing individual interactions. Think of it like driving on a highway where the speed limit was higher decades ago. Cars still followed traffic rules, just under different constraints. The debate intensifies when we consider alternative theories like loop quantum gravity or string theory, where space-time's fundamental properties might have evolved over cosmic history. In some models, the fabric of space was stiffer in the early universe, allowing disturbances like light to propagate faster, similar to how vibrations travel quicker through a taut guitar string than a slack one. If future observations of distant quasars or gravitational waves reveal subtle discrepancies in propagation times, they might offer the smoking gun for this controversial idea. For now, the constancy of light speed remains mainstream science's hill to die on. But the fact that serious physicists entertain alternatives speaks volumes about the depth of our cosmic puzzles. Whether a historical speed boost for photons holds up or not, its mere proposal highlights how even our most cherished constants might just be placeholders waiting for a deeper truth to emerge from the darkness. Einstein famously dismissed quantum entanglement as spooky action at a distance, baffled by particles that instantly influence each other across vast reaches of space. But here's the cosmic twist: the universe itself performs a similar trick on a grand scale. When space expands, it doesn't push galaxies apart like objects on a conveyor belt. Instead, every region of space stretches simultaneously, creating a coordinated separation that happens everywhere at once. It's as if the fabric of reality itself is entangled, with distant points responding to cosmic expansion in perfect, instantaneous harmony, no signal or force traveling between them. Think of it like a rubber sheet dotted with coins. Stretch the sheet, and every coin moves away from every other coin, not because they're sliding across the rubber, but because the space between them is expanding uniformly. No coin tells its neighbor to move. The change happens holistically, a synchronized dance orchestrated by the stretching of the sheet itself. Now replace those coins with galaxies and the rubber sheet with space-time, and you've got cosmic expansion's eerie parallel to quantum entanglement. Both phenomena defy classical intuition about how information or influence should propagate, whether it's entangled particles mirroring each other's states faster than light or galaxies drifting apart without any local motion. The key difference: quantum entanglement links specific particles through mysterious, invisible threads, while cosmic expansion is a global property of space itself. Yet both share a profound lesson. Reality doesn't always play by the rules of cause and effect we're used to. In quantum mechanics, entangled particles seem to know each other's states instantly, ignoring the speed of light limit. In cosmology, galaxies recede from each other not because they're moving through space, but because space is growing between them, a distinction that means their apparent separation speed can exceed light's velocity without violating relativity. This parallel becomes even stranger when you consider the horizon problem, the puzzle of why far-flung regions of the universe look so similar. Inflation solved part of it by stretching space faster than light, but the deeper mystery remains: how did these regions agree on their properties without time to communicate? Quantum entanglement offers a tantalizing hint. If the infant universe was a seething quantum foam, its particles might have been entangled before inflation magnified them to cosmic scales, imprinting matching patterns across the sky like echoes of an ancient connection. Here's where the science gets speculative but thrilling. Some theories propose that spacetime itself emerges from a quantum network of entangled particles, meaning the universe's expansion could literally be the unraveling of a vast, invisible web of quantum links. Others suggest dark energy's repulsive force might stem from the gradual decoupling of these primordial entanglements, as if the cosmos is slowly forgetting its deepest bonds. While these ideas are far from proven, they highlight a breathtaking possibility. The same quantum weirdness governing atoms might also shape the fate of galaxies. The takeaway isn't just an academic curiosity. It's a reminder that the universe loves to repeat its tricks across scales. What we call spooky in the quantum realm might just be the same cosmic choreography we observe in the stretching heavens, a hidden unity between the smallest and largest things we know. And if that's true, then solving one mystery could unlock the other, revealing a reality far more interconnected than we ever imagined. Whether through quantum threads or stretching space, the cosmos keeps showing us that distance and separation might just be illusions, artifacts of a deeper, stranger connectedness we're only beginning to glimpse. What if everything you see around you, the stars, the galaxies, even the screen you're staring at right now, is nothing more than a shadow, not a physical object but a projection, like a hologram cast from the edges of reality itself? This isn't science fiction, it's a serious theory called the holographic principle, and it suggests our three-dimensional universe might be encoded on a two-dimensional surface at its boundary, with cosmic expansion unfolding like lines of data being written onto that vast cosmic hard drive. The idea starts with black holes. In the 1970s, physicist Jacob Bekenstein discovered something startling: the amount of information a black hole can contain isn't proportional to its volume, but to its surface area. It's as if all the data about what falls into the abyss gets compressed and stored on its event horizon, like a cosmic USB drive. This led theorists like Gerard T. Hooft and Leonard Susskind to propose a radical extension. What if the same principle applies to the entire universe? Instead of information being scattered throughout space, it could be etched onto a distant, two-dimensional boundary, with our 3D reality emerging from it like a movie projected from a flat screen. Imagine standing in front of a waterfall. The cascading water seems solid, full of depth and motion, but in reality, it's just countless individual droplets interacting in precise ways. The holographic principle suggests our universe works similarly. What we perceive as three-dimensional space might just be an intricate illusion, with the true source code of reality existing on some unimaginably distant surface trillions of light-years away. Even expansion could be part of this cosmic encoding. As the universe grows, it's not space itself stretching, it's the information at the boundary updating, rewriting itself to include more volume, like a computer rendering a larger virtual world. This might sound abstract, but the math holds surprising weight. In the late 1990s, string theorists discovered that equations describing a hypothetical 5-dimensional universe perfectly matched those for a 4-dimensional one, as if the extra dimension was an emergent property, not fundamental. It's like realizing a perfectly detailed 3D video game is actually running on a 2D graphics card. The richness we see isn't stored where we think it is. Applied to cosmology, this could mean dark energy isn't a force permeating space, but a side effect of how information on the boundary evolves over time. Critics argue the holographic principle is untestable. How do you prove we're living in a projection? Yet some experiments offer tantalizing hints. When physicists analyze the cosmic microwave background, they find its fluctuations match predictions for a universe with limited information density, like pixels on a screen. There's also the baffling fact that the universe's total information content never exceeds what could fit on its surface area, as if space itself obeys a cosmic storage limit. If true, this reshapes our understanding of expansion in mind-bending ways. The accelerating universe might not be stretching because of dark energy, but because the resolution of our hologram is increasing, creating the illusion of more space. Distant galaxies receding faster than light, just day to being written to new sectors of the cosmic hard drive. Even time dilation could be a rendering effect, clocks ticking slower in strong gravitational fields because the system needs more processing power to simulate them accurately. The wildest implication, it could mean reality as we know it is fundamentally informational. Space, time, matter, all might be secondary to the bits and codes operating at the boundary. We're not just living in a universe, we might be living inside a computation, with expansion as the cursor moving steadily forward, writing the next frame of existence into being. And if that sounds unbelievable, remember the universe has never cared much for what we find easy to accept. Dark matter is the unseen architect of the cosmos, a hidden hand that sculpted the universe's structure long before stars or galaxies even existed. While it doesn't interact with light or ordinary matter directly, its gravitational pull is the reason galaxies cluster the way they do, forming vast webs and filaments instead of scattering randomly like sand in the wind. Without dark matter's invisible scaffolding, the universe would look radically different, and so would our ability to measure its expansion. Here's how it works. In the early universe, dark matter's gravity acted like a cosmic magnet, attracting hydrogen and helium gas into dense clumps. Over billions of years, these clumps grew into galaxies, with dark matter forming massive halos around them like invisible cocoons. The distribution of these halos, how close or far apart they are, holds crucial clues about expansion. When astronomers measure how fast galaxies move away from us, they're not just tracking the stretch of space between them. They're also accounting for the way dark matter's gravity tugs on those galaxies, subtly altering their trajectories. Think of it like measuring the speed of boats drifting on a rising tide. If some boats are anchored to hidden weights below the surface, weights we can't see but know must be there, their movement won't perfectly match the water's flow. Dark matter is those hidden weights. By mapping the peculiar motions of galaxies, how they deviate from the smooth expansion predicted by Hubble's law, scientists can reverse engineer the distribution of dark matter. The more precisely they measure these deviations, the more accurately they can calculate the universe's expansion rate, accounting for dark matter's gravitational interference. This gravitational dance isn't just happening on small scales. The largest structures in the universe, colossal galaxy clusters and superclusters, are also shaped by dark matter's pull. When astronomers study how these clusters bend light from background galaxies, a phenomenon called gravitational lensing, they're essentially weighing the dark matter within them. The heavier the cluster, the more it distorts space-time, and the more it resists the universe's expansion in its local region. These measurements provide independent cross-checks on expansion rates, revealing whether dark energy's push is winning against dark matter's tug. The irony is profound. Dark matter, which makes up 27% of the universe's mass energy content, doesn't directly influence expansion. But by structuring the cosmos, it gives us the landmarks we need to measure that expansion accurately. Without it, galaxies might be so evenly spaced that Hubble's law would be nearly impossible to discern, or so chaotically arranged that no clear pattern would emerge. Instead, dark matter created the perfect cosmic middle ground, a universe lumpy enough to study but orderly enough to decode, and here's where it gets even more fascinating. Some of the most precise measurements of dark matter's distribution come from the cosmic microwave background, that ancient light we discussed earlier. The slight temperature variations in that glow reveal how dark matter was clustered in the infant universe long before galaxies formed. When combined with modern galaxy surveys, this data creates a timeline of dark matter's role in cosmic evolution, showing how its gravitational blueprint guided the universe from smooth simplicity to the intricate web we see today. Ultimately, dark matter's greatest gift might be its silence. It doesn't emit or absorb light, but its gravitational whispers shape everything we observe. By listening to those whispers through galaxy motions, gravitational lensing, and the echoes of the Big Bang, we've uncovered not just the hidden structure of the cosmos, but also the subtle ways expansion weaves through it. Dark matter doesn't just hide in the shadows, it paints the canvas we use to measure the universe's growing edges. The cosmic microwave background is supposed to be the ultimate equalizer, a near-uniform glow from the infant universe that looks the same in all directions. But when scientists mapped its subtle temperature variations with unprecedented precision, they stumbled upon something unsettling. Hidden in the data was a bizarre alignment of hot and cold spots, arranged along a specific axis in space like some cosmic spine running through the universe. Dubbed the axis of evil by a skeptical physicist, this strange pattern defies everything we know about cosmic symmetry and hints that either our universe isn't as random as we thought, or something fundamental in our models is missing. At first glance, the anomaly seems innocuous, just a slight preference for temperature fluctuations to line up along a particular plane. But statistically, this alignment is about as likely as flipping a coin 1,000 times and getting heads every single time. According to the standard cosmological principle, no direction in space should be special. The universe should appear roughly the same whether you're looking left, right, up, or down. Yet the CMB's fluctuations seem to whisper that one axis might be curiously privileged, like a hidden compass pointing toward something we can't yet see. Theories to explain this oddity range from mundane to mind-bending. One possibility is that our galaxy's motion through space is distorting the CMB in ways we haven't fully accounted for, like a passenger on a train mistaking raindrops streaking across the window for some grand atmospheric pattern. Others suggest it could be evidence of an ancient gravitational wave from the universe's first moments, a primordial ripple that left its imprint on the CMB like a fingerprint pressed into cooling wax. But the most radical idea, that the axis of evil is a relic of something before the Big Bang, a cosmic structure or anisotropy that survived whatever process birthed our universe, etching a phantom signature into the very first light. Imagine finding a mysterious symbol carved into the foundation stones of every civilization on Earth. The axis of evil might be that symbol, a clue that our universe inherited properties from a predecessor, like an heir unknowingly carrying the birthmark of a long-dead ancestor. Some models of cyclic cosmology, where universes are born and reborn in endless cycles, predict such imprints could persist across cosmic resets. Others speculate it's evidence of a multiverse, where neighboring universes exerted gravitational tugs on ours during inflation, warping its structure like invisible hands molding clay. The implications are profound. If the axis of evil is real, not just a statistical fluke or measurement artifact, it could mean the universe has a preferred direction, breaking one of cosmology's most cherished symmetries. Expansion might not be perfectly uniform. Dark energy's push could vary along different axes, subtly shaping the cosmos like an invisible sculptor. Future missions like the European Space Agency's CMB-S4 experiment aim to test these ideas with even sharper precision, scanning the microwave sky for corroborating patterns. For now, the axis of evil remains an enigma, a whisper of something beyond our current understanding, lurking in the oldest light we can see. It's a reminder that for all our maps and measurements, the universe still holds mysteries that defy simple explanations. And if this axis turns out to be more than a cosmic coincidence, it might not just challenge our models, it could rewrite the story of how everything began. Black holes aren't just cosmic vacuum cleaners, they're also the universe's ultimate shredders, swallowing stars, planets, and even light itself, leaving no trace of what fell in. Or so we thought. The black hole information paradox is one of the most heated debates in physics, centered on a simple but devastating question. When matter vanishes into a black hole, does the information it carried, the quantum states that defined its particles, truly disappear forever? Quantum mechanics says no, information can't be destroyed. General relativity says yes, black holes erase it irretrievably. This contradiction has baffled physicists for decades, but cosmic expansion might hold a clue, because dark energy's relentless stretching of spacetime could be silently preserving that lost information in ways we're only beginning to grasp. Here's the problem in a nutshell. Imagine tossing a book into a fire. The pages burn, but the information, the words, the story isn't truly gone. It's just transformed into heat, smoke, and ash, scattered in ways that are theoretically reversible if you could track every particle. But toss that same book into a black hole, and according to Einstein's equations, it's gone for good. The black hole's gravity is so intense that not even the book's atomic structure survives intact. Over time, the black hole evaporates via Hawking radiation, leaving behind no fingerprints of what it consumed. This violates quantum mechanics' bedrock principle. Information must always be preserved, never erased. The paradox has led to wild theories, from holographic universes to parallel realities inside black holes. Now enter dark energy. As space expands, it doesn't just push galaxies apart, it stretches the very fabric of spacetime, imprinting every passing photon with subtle shifts in wavelength. Some theorists suggest this stretching could act like a cosmic backup drive, encoding information from particles that fell into black holes onto the stretched spacetime itself. Picture dipping a sealed message into a jar of honey, then slowly pulling it out. The honey's viscosity would distort the message, but a sharp eye could still reconstruct it from the streaks left behind. Similarly, as spacetime stretches, quantum information from devoured particles might leak into the expanding universe, preserved in the geometric wrinkles of spacetime's fabric. This idea dovetails with the holographic principle, which posits that all the information in a volume of space can be represented as encoded data on its boundary, like a 3D movie projected from a 2D screen. If true, black holes might not destroy information after all. They could simply transfer it to the edges of the universe via expansion, where dark energy's push keeps it intact but hopelessly scrambled. It's as if the universe has a fail-safe mechanism. When information risks being erased locally, cosmic expansion saves it globally, like a librarian reshelving books in a library that never stops growing. The implications are staggering. If dark energy plays a role in solving the information paradox, it would mean the universe's acceleration isn't just a footnote in cosmology. It's a vital part of how reality preserves its own history. Every time a black hole swallows a star, expansion could be silently storing that star's quantum signature in the stretched spacetime between galaxies, ensuring nothing is ever truly lost. Future civilizations might even develop ways to read this cosmic archive, decoding the universe's expansion patterns like forensic scientists reconstructing events from scattered evidence. Of course, this is speculative. No experiment has yet detected information leaking from black holes via spacetime stretching, but the mere possibility reshapes how we view dark energy. It's no longer just a mysterious force driving galaxies apart. It could be the universe's way of balancing the books, ensuring that even in the face of annihilation, the story of existence never loses a single page. And if that's true, then the answers to some of physics' deepest questions might not lie in the depths of black holes after all, but in the vast, stretching void between them. Neutrinos are cosmic ghosts, particles so elusive they pass through planets like moonlight through glass. For decades, physicists assumed these nearly massless particles couldn't possibly influence the universe's grand structure. Then came the shock. Neutrinos do have mass, not much. A single neutrino might weigh less than a billionth of an electron. But when you consider that trillions stream through your body every second, their collective gravity starts to matter. This discovery isn't just a particle physics curiosity, it's rewriting how we model cosmic expansion and the very formation of galaxies. Here's why. In the early universe, neutrinos raced around at nearly light speed, their kinetic energy overwhelming gravity's pull. Like hyperactive children refusing to sit still, they couldn't clump together to form structures the way dark matter and ordinary matter did. Instead, they smoothed out density fluctuations, acting as cosmic sandpaper on the primordial universe's rough edges. The heavier neutrinos are, the more they suppress the growth of galaxy clusters, leaving an imprint we can now detect in the universe's large-scale structure. Modern sky surveys reveal slightly fewer galaxy clusters than our models predict, and neutrinos' newfound mass might finally explain why, but the plot thickens. Neutrinos' mass also tweaks the universe's expansion rate. As the cosmos stretched, these particles transitioned from zipping around like ultra-relativistic speedsters to moving sluggishly as their kinetic energy reddened with the expanding universe. This shift altered how their energy contributed to the cosmic budget, effectively changing the equation for how fast space could stretch. Some calculations suggest that properly accounting for neutrino masses could nudge our measurements of the Hubble constant, potentially easing tensions between conflicting expansion rate estimates. It's like realizing you've been miscounting a hidden currency in your household budget. Suddenly, the numbers make more sense. The real surprise, neutrinos might not all weigh the same. Experiments like Japan's supernovae and have found evidence that the three known types, electron, muon, and tau neutrinos, have different masses, though the exact hierarchy remains hotly debated. This neutrino mass ordering problem isn't academic. It changes how these particles sculpted the cosmos. If neutrinos follow a normal hierarchy with the lightest mass state being electron neutrinos, their impact on galaxy formation would differ subtly from an inverted hierarchy. Future telescopes like the Vera Rubin Observatory could spot these differences in the clustering of distant galaxies, turning the sky itself into a neutrino scale. What's wildest about this cosmic subplot is how it connects the unimaginably small to the astronomically large. Particles so tiny they barely interact with anything have subtly steered the evolution of galaxy superclusters. Their fingerprints hide in the voids between galaxies and the peculiar motions of distant stars. And as we refine our measurements of neutrino properties, we might uncover even deeper links, perhaps even clues about why the universe's expansion started accelerating in the first place. So next time you feel a sunbeam on your skin, remember, it's carrying neutrinos born in the solar core, particles that once coursed through the infant universe and helped shape everything you see. They're not just cosmic afterthoughts, they're silent architects, and we're only beginning to read their blueprints. What if dark energy isn't real, and the universe's accelerating expansion comes down to gravity itself playing by different rules than we thought? Enter modified Newtonian dynamics, or a radical idea that suggests we don't need invisible forces to explain cosmic expansion. Instead, perhaps Einstein's theory of gravity, while brilliant, is subtly incomplete on galactic scales. At its core, Mund proposes that gravity behaves differently when it's extremely weak, like the faint tugs between distant galaxies, compared to the stronger pulls we're familiar with in our solar system. It's as if the universe has two rulebooks for gravity, one for nearby, high-stakes interactions and another for the whisper-thin forces governing cosmic expansion. The roots of this idea trace back to the 1980s, when astronomer Mordechai Milgrom noticed something peculiar about rotating galaxies. According to Newton's laws, stars on the outer edges should move slower than those near the center, just as Pluto orbits the Sun more sluggishly than Mercury. But observations revealed the opposite stars at galactic edges raced just as fast as inner ones, as if some unseen mass were tugging on them. Dark matter became the go-to explanation, but Milgrom offered an alternative. Maybe gravity doesn't weaken as sharply with distance as we've assumed. Below a certain threshold, around 1/10,000,000th of the acceleration we feel from Earth's gravity, the force could transition to a gentler decline, propping up those unexpectedly speedy stars without invoking invisible matter. When applied to cosmic expansion, implications grow even more provocative. If gravity's strength changes at these faint scales, it could mimic the effects of dark energy, creating the illusion of accelerating expansion without any mysterious repulsive force. Picture blowing up a balloon where the rubber stretches more easily at larger sizes, making it seem like an unseen hand is inflating it faster. That's essentially how one might explain the universe's runaway growth, not through dark energy's push, but through gravity's pull becoming unexpectedly weaker over vast distances. But Mund isn't without cracks. While it neatly explains galaxy rotation curves, it struggles with other observations like the Bullet Cluster, where colliding galaxies clearly show gravitational effects from unseen mass. Supporters counter that these discrepancies might hint at even deeper modifications to gravity or undiscovered nuances in how matter behaves. Some theories, like tensor vector scalar gravity (TVS), weave relativity into Mund framework, attempting to reconcile it with cosmic phenomena like gravitational lensing. Others, like emergent gravity, propose that gravity isn't a fundamental force at all, but a side effect of entropy like cosmic friction emerging from the universe's inherent disorder. The debate boils down to a philosophical split. Dark energy and dark matter preserve Einstein's gravity by adding new ingredients to the cosmic recipe. Mund and its cousins tweak the recipe itself, arguing that simpler adjustments might explain more. Both approaches have predictive power and blind spots. For now, most cosmologists favor the dark energy paradigm, but Mund lingers as a tantalizing what-if, reminding us that even our most cherished theories might just be approximations of a deeper truth. What's fascinating is how these competing ideas push science forward. Whether gravity's laws need revising or invisible energies dominate the cosmos, each possibility forces us to ask better questions, design sharper tests, and ultimately inch closer to understanding the universe's greatest mystery, why it's rushing away from itself at all. And in that tension between the known and the unknown lies the thrill of discovery. The universe isn't just expanding, it's reshaping the very architecture of reality itself. Picture the cosmic web, that magnificent lattice of galaxies strung along invisible filaments of dark matter, each intersection marked by glittering superclusters. For billions of years, gravity has sculpted this intricate tapestry, drawing matter into sprawling highways of star-filled nodes and vast, empty voids. But dark energy is slowly unraveling it all, stretching those filaments like threads in an infinite loom until the universe's grand design dissolves into isolated islands adrift in an ever-darkening sea. This transformation unfolds over timescales so vast they defy imagination. Today, galaxies along a single filament might be separated by a few 100 million light-years, still connected by tendrils of gas and dust. Fast forward 1 trillion years, and expansion will have pulled those threads so thin that the space between them becomes uncrossable. Clusters like our local group will remain bound by gravity, but everything beyond will redshift into invisibility, their light stretched beyond detectability. What was once a bustling cosmic metropolis will become a lonely archipelago, each cluster unaware of the other's existence. The mechanics behind this isolation are as relentless as they are simple. Dark energy's repulsive force doesn't just push galaxies apart, it stretches the very space between them, like a baker tugging at cosmic dough until it tears. Filaments that once channeled rivers of gas to feed growing galaxies will snap, starving future stars of fuel. Voids, already vast today, will balloon until they swallow 99.9% of the observable universe. The Virgo supercluster, which currently houses the Milky Way among its 1,000 galaxies, will be the last structure we ever see beyond our immediate neighborhood. Here's the haunting part: this process isn't something far-flung civilizations will witness in some distant future. It's already happening. Light emitted by galaxies at the universe's current edge will never reach us. They've already crossed the expansion horizon, their farewell photons just now arriving after billions of years of travel. Future astronomers born in 100 billion years won't even know other galaxy clusters exist. Their night sky will show only the merged remnants of Andromeda and the Milky Way, a single, aging elliptical galaxy surrounded by blackness, with no clue that trillions of others once glittered beyond it. Yet, even as expansion disassembles the cosmic web, echoes of its structure linger. The baryon acoustic oscillations we discussed earlier, those frozen sound waves from the early universe, will remain imprinted in the distribution of matter like ghostly footprints. And in the far future, if any civilizations survive, they might decode those patterns to reconstruct what the universe once was. A vibrant, interconnected network of galaxies now lost to the stretching dark. This slow-motion dissolution forces a profound realization. The cosmic web isn't just a snapshot of the universe's structure. It's a transient masterpiece, a fleeting alignment of matter and energy that will never recur. We're living in the brief era where its grandeur is still visible, where light from distant clusters still reaches us, carrying stories of a time before isolation. It's our incredible luck, or perhaps our tragedy, to exist in the cosmic sweet spot when the universe is both old enough to be interesting and young enough to still show its hand. For most of cosmic history, dark energy has been a whisper in the background, a faint pressure barely noticeable against gravity's relentless pull. But around 5 billion years ago, something shifted. This mysterious force began to dominate, accelerating the universe's expansion in what astronomers call the cosmic jerk. The puzzling part: why then? Why not earlier or later? That's where time-varying dark energy theories come in. The radical idea that dark energy isn't a constant, but a dynamic player whose strength evolves as the universe ages. Imagine a dimmer switch slowly turning up the light. In some models, dark energy behaves similarly, growing stronger as space stretches. Its energy density might have been insignificant when galaxies first formed, overshadowed by matter's gravitational clumping. But as expansion diluted matter's influence, dark energy's push became impossible to ignore, like a breeze turning into a gale as trees thin out. Other theories propose the opposite. Dark energy was once stronger, then decayed to its current level. Picture a battery draining over cosmic time, its voltage dropping until it reaches the precise level needed to kickstart acceleration 5 billion years ago. The implications are staggering. If dark energy's strength shifts, the universe's fate could be far stranger than we've imagined. A strengthening version might lead to the Big Rip, tearing apart galaxies long before heat death's slow fade. A decaying one could see gravity regain control, collapsing the cosmos in a big crunch. Even more intriguing are quintessence models hypothetical fields that fluctuate like invisible weather systems, with dark energy's intensity waxing and waning across epochs. Some variations even allow for temporary hiccups where expansion briefly slows before lurching forward again. Clues to these possibilities hide in supernova data. Distant explosions from 10 billion years ago, when dark energy was weaker, should appear brighter relative to their modern counterparts if the force has grown over time. Conversely, if dark energy is decaying, those ancient supernovae would look dimmer than expected. Current observations tentatively favor a near-constant dark energy, but the margins of error leave room for surprises. Future telescopes like the Vera Rubin Observatory could spot subtle deviations in supernova brightness patterns, revealing whether dark energy is truly steadfast or a shape-shifter in cosmic disguise. What's fascinating is how these theories reframe the universe's biography. A time-varying dark energy suggests cosmic history isn't just a linear march toward emptiness, it's a story with plot twists where the protagonist's nature changes in Act 3. And if that's true, we might be living in a special chapter, the brief window where dark energy's push is strong enough to notice, but not so overwhelming that it erases all other cosmic drama. The next generation of sky surveys won't just map the universe, they'll read its pulse, searching for the heartbeat of a force that might still be finding its strength. Here's a cosmic riddle that will twist your perception of reality. What if everything you see, everything you remember, even your very existence right now isn't real? Not in the sense of a simulation or a dream, but as a fleeting accident of particle physics, a momentary flicker of order in an endless sea of chaos. This is the Boltzmann brain paradox, a thought experiment so unsettling it makes the universe's expansion feel like a ticking time bomb for logic itself. The paradox starts with entropy, the universe's tendency toward disorder. In the 19th century, physicist Ludwig Boltzmann proposed that even in a chaotic system, random fluctuations can create pockets of order by pure chance. Imagine a box of gas where all the molecules happen to cluster in one corner for a split second, defying the odds. Now scale that up to the cosmic level. Given enough time, and the universe has near infinite time statistically, anything that can happen will happen, no matter how improbable, including the spontaneous assembly of a fully formed, self-aware brain, complete with false memories of a life that never existed. Here's where expansion turns this from a quirky hypothetical into a terrifying possibility. As dark energy accelerates the universe's growth, matter and energy become so diluted that organized structures like stars, planets, and brains can no longer form naturally. But in this cold, empty future, random quantum fluctuations become the only game in town. Given eternity, the odds shift. It becomes statistically more likely for a lone, disembodied brain to pop into existence from the void, complete with the illusion of a past and a present, than for an actual civilization like ours to evolve the old-fashioned way. Think of it like shaking a jar of alphabet soup forever. Eventually, the letters will randomly spell a coherent sentence. Now imagine that sentence is you, your thoughts, your senses, your certainty that the world around you is real. The Boltzmann brain scenario suggests that in an eternally expanding universe, there should be vastly more of these phantom observers than real ones. So why trust that you're not one of them? The implications are dizzying. If Boltzmann brains dominate the cosmic long run, then everything we perceive, the laws of physics, the history of the universe, even the chair you're sitting on, could just be a hallucination of particles that momentarily arrange themselves into a thinking pattern. Expansion doesn't just isolate galaxies, it might make genuine sentience an anomaly, a brief spark in a darkness where false consciousnesses outnumber real ones 1,000,000,000,000 to 1. Physicists have proposed wild solutions to this paradox, from arguing that quantum mechanics prevents such fluctuations to suggesting our universe's expansion won't last long enough for Boltzmann brains to dominate. Some even turn the argument on its head. The fact that we observe an ordered universe now might imply dark energy's acceleration will eventually stop preserving reality's integrity. But the deeper lesson remains. The universe's expansion isn't just a fact to measure. It's a mirror reflecting back uncomfortable questions about what's real, what's possible, and whether the cosmos itself is playing tricks on us. Let's pause for a moment and take stock of the cosmic roller coaster we've just ridden. The universe isn't just expanding, it's accelerating, propelled by a mysterious force called dark energy that makes up 68% of everything. Distant galaxies aren't merely drifting away, they're vanishing beyond an invisible horizon, their light stretched into oblivion by the relentless stretching of space itself. And perhaps most mind-bending of all, the farther we look, the faster those galaxies appear to race from us, as if the cosmos is unraveling at the seams, rewriting the rules of reality with every passing second. Yet for every answer we've uncovered, a deeper mystery lurks. What is dark energy? Is it the cosmological constant Einstein accidentally predicted, or something far stranger? A phantom force growing stronger with time, destined to tear apart atoms in a big rip. Could cosmic expansion be hinting at hidden dimensions, a multiverse, or even flaws in our understanding of gravity itself? The Hubble tension, that stubborn mismatch in expansion measurements, tells us we're missing something fundamental. Maybe it's neutrinos with unexpected mass, or voids like the KBC billion light-year emptiness skewing our cosmic perspective. Or perhaps, as the holographic principle suggests, we're all just shadows cast from the edge of reality. Here's the humbling truth. We're piecing together this puzzle with fragments of light from supernovae, whispers of sound waves frozen in the infant universe, and the eerie glow of the cosmic microwave background. Every clue pulls us deeper into the unknown. The universe doesn't owe us clarity, it's a riddle wrapped in expanding space-time, and we're only beginning to read the first lines. So now it's your turn. Which fact shattered your view of reality? Was it the Boltzmann brain paradox, where your own consciousness might be a statistical fluke? The cosmic jerk 5 billion years ago that kicked expansion into overdrive? Or the spine-chilling possibility that one day, every galaxy beyond our own will disappear, leaving future astronomers in an island universe of darkness? Drop your mind-blown moments in the comments. I'll be right there geeking out with you, because here's the beautiful, terrifying, exhilarating takeaway. We're not just observers of this grand cosmic story. We're part of it, riding an expanding bubble of space-time, hurtling toward a future we can't yet imagine, armed with nothing but curiosity and the light of distant stars to guide us. The adventure is just beginning, and the next chapter might rewrite everything we think we know.